Question 9. This question is about ethanoic anhydride. In the gas phase, ethanoic anhydride decomposes from ethanol. The equation is CH3CO2O arrows H2C double 1C double 1O plus CH3COOH. Ethanol is the simplest member of the ketene homologous series. Ketenes all contain one C double bond C and one C double bond O. And then it says, deduce the general formula for the ketene homologous series. It's going to be CnH2n minus 2 and oxygen, O. So CnH2n minus 2O. CnH2n minus 2O. Then figure 9.2, figure 11 shows an incomplete suggested mechanism for decomposition of ethanoic anhydride. Complete the mechanism, adding 3 curly arrows any relevant lone pairs of electrons. So 3 curly arrows. So first things first, we can see that this carbon from here to here, we've got this carbon positive, this oxygen has a negative charge, and that's that oxygen. So what actually happens is a curly arrow from CO to the oxygen. Now it breaks up, the carbon's positive, the oxygen is negative. And now what happens is now the oxygen that is negative has a lone pair of electron, and then goes here, takes a hydrogen, and now the left carbon has a spare electron. It wants to form a double bond. Then it forms a double bond, OH. This hydrogen bonds with this oxygen with lone pair of electron negative to form OH, and that's it. So one curly arrow from middle of CO bond to the oxygen, one curly arrow from the lone pair of electrons on the oxygen which is negative to the hydrogen, and then now the left carbon has a spare electron, wants to reform the double bond. And that's it. And then it says 9.3 and 9.4. 9.3, for chemical reaction, the relationship between the rate constant and the temperature T is shown by the Arrhenius equation for decomposition of gaseous ethanoic anhydride. Activation energy is that. Arrhenius equation constant A is that. At temperature T1, the rate constant K is that. Calculate T1. Now there's 2 ways we can do this, but I'm going to do it via the way where we take the log. So lnk equals lna minus ea over RT. lnk equals lna minus ea over RT. So now what do we actually want to find? We want to find the temperature, which is here. So we want to, so then we can do ea over RT equals ln minus lnk. Then we can do ea equals lna minus lnk brackets RT. Then we can do RT equals ea divided by lna minus lnk. And then to find out T, all we're going to do is ea divided by lna minus lnk, and then whatever we get from that, divide it by R, which is 8.31, and then divided by 8.31, and that will give us T1. Okay, or you can put the 8. So now let's substitute values in. So EA is 34.5 kilojoules, but because the gas constant R is in joules, we need activation energy also to be in joules, so it's going to be 34,500 divided by ln 1.00 times by 10 to the power of 12, ln 1.00 times by 10 to the power of 12 minus ln k, ln 2.48 times by 10 to the power minus 8, minus ln 2.48 times by 10 to the power of 8. So now, that's in the calculator. So 34,500 divided by shift log 1.0 times by 10 to the power 12 minus shift ln 2.48 times by 10 to the power 8. So one sec, 34,500 divided by, yep, ln a 1.0 times by 10 to the power 12 then we get 500. Therefore the temperature of T1 is 500 Kelvin. We don't need to add 273 to Kelvin. Kelvin is already in Kelvin. And then 9.4, sketch the Maxwell-Boltzmann distribution curve at temperature T1 at the high temperature T2. Include a label for each axis, mark an appropriate axis typical position for the activation energy, and explain why the rate of reaction is faster at T2. So we should know already. We need to have arrow here and arrow here. It's not necessary, I don't think. But number of molecules. Number of molecules. Number of molecules, and then energy, or kinetic energy, would say energy. Kinetic is not required in the small scheme. So number of molecules, that does not look like molecules. Number of molecules. Energy. The activation energy is somewhere around about here. And we'll just do a dotted line. And now at T1, normal temperature, it's just going to look something, maybe it should have been a bit higher, it's just going to look something like this, right? Let's get rid of that. And now at a high temperature T2, it's going to be more steeper, but then it's going to fall here, and then eventually it's going to be, so the peak, so this is the T1 and high temperature T2, and explain why the rate of reaction is faster at T2. Well, because it's because more particles have energy greater than or equal to the activation energy. More particles have energy greater than or equal to activation energy. And also make sure that the EA, the activation energy, is on the x-axis. Don't put it up here, which I could see myself making mistakes. Probably have made that mistake before, but yeah, put it on the x-axis. Energy, number of molecules, and try your best to sketch it properly. Obviously mine's not great. And then do a dotted line for activation energy to show activation energy, and then why the rate of reaction is faster at T2, because more particles have energy greater than or equal to activation energy at T2. And that is the end of question 9.